Thanks for joining me. This will be a very short lesson and we're going to discuss the states of matter. So clearly, I think from earlier studies in science you've learned that matter can exist as a solid, a liquid, or a gas. Now there are two other states of matter that scientists believe exist. One is called plasma. It has nothing to do with your blood, but it has to do with ionized matter. And another one is called a neutron star, where it's like a spoonful of a neutron star type of matter would weigh as much as the Earth. So we're not going to deal with plasma, we're not going to deal with neutron stars. We'll just stick with solid, liquid, and gas for our class. Now, I think you know in a solid, the atoms are held close together, and even though they might move slightly and vibrate a little bit, to the naked eye, they tend not to be moving at all. And so they're locked in position. In a liquid, the materials, the atoms are moving a little bit faster, and they will tend to still stay together, but they'll move very easily. And let's compare that to a gas. In a gas, the molecules are moving very fast, and they will fill whatever size container they're in, which is why we need to put a cap on this one here, or the gas molecules might potentially escape out of the bottle if they're less dense than air. So in a solid, we know solid generally is the densest or most dense state of matter. Now that's true for all substances except water. For water, a solid water is less dense than liquid water. And that has to do with the way that the molecules of water orient themselves. They actually link together. There's an H2, those two blue ones, and an O next to another H2 and an O, and they end up trapping air in between those molecules. And this is what makes very pretty little snowflakes on the right weather kind of day, and it's also what traps air in there. If you've ever dissolved something like sugar or salt in water, it fits in these little pockets, these little holes. They're called interstitial spaces. Now, here we're looking at ice again. You're looking at water. It's H2O, and they're bonded to a bunch of other waters. And you can see these little blue dots are a very weak attraction between the hydrogen of one atom and an oxygen of another. They're called hydrogen bonds. That's a type of chemical bond we'll discuss later on in the year. They're very important. They're what allow two water molecules to like stick together. And because they stick together, you can pour water into a glass and get the water to go over the glass without spilling. It's also what allows a bug to walk on the surface of water because the hydrogen bonds hold the water together. Now, if you want to be a really a mean person, you can take a bar of soap and touch it to the surface of the water where a bug is on the top of the water near you, and soap is a surfactant or a surface acting agent, and it will break the hydrogen bonds and allow the bug it'll sink and fall below the surface. Now, I would suggest a better way to do that demonstration would be to take a cup of water, take a small piece of tissue paper, and then you can take like a straight pin, and then have the tissue paper, and then put the straight pin on top of it, and rest that on the surface of the water. And what will happen is the paper will absorb water, will wet out, and will sink, and you'll be left with the pin sitting on the surface of the water. And then if you want, you can add a drop of soap very carefully to the edge, and that pin will sink. Or if you don't have a pin and no toilet paper, that's a bigger issue. If you don't have the toilet paper, we'll just take a cup of water and sprinkle pepper on it, and then it'll float on top. Add a drop of soap, and the pepper will sink. And again, this is due to these little blue dots. We call that hydrogen bonding. It's a weak electrostatic attraction between two atoms that have different polarities. Here we have liquid water. Notice that these water molecules are a little bit closer together than the solid ones because, again, liquid water is more dense than solid water. So in a liquid, even though it might not look like the molecules are moving, they are in motion, right? We talked about if you take hot water and then put a drop of food coloring in it, it will mix relatively quickly even though you didn't stir it. And if you take cold water, ice cold water, and put a drop of food coloring in, it'll mix much slower. And that's evidence then that molecules are in constant motion. And in the liquid state, there are more intermolecular forces between these atoms. We'll discuss intermolecular and intramolecular forces at a later time. And so the molecules are very close together, and because they're close together, when you push on a liquid, it does not compress. Gases can be compressed, but liquids, the atoms are already pretty close together. They're just not stuck together. So liquids are pretty much non-compressible or incompressible. And liquids will stay wherever you put them. They don't necessarily fill the container like a gas would. Here's that little bug floating on the surface of water. And again, I'm not cruel enough, but if I had a bar of soap, I probably would be tempted to touch to the water and watch the bug sink. In a gas, the molecules are excuse me, very far apart, and they tend to fill the container that they are in, and they are in constant motion. Water in the gaseous state we call steam. Now, here's a couple terms we want to make sure we understand: evaporation and condensation. So look at what happens to these water molecules down here. Right now, they're in the liquid state, but they absorb some energy, and when they absorb energy, they evaporate. They move from the liquid state to the gaseous state. And once they're in the gaseous state, they might lose energy, in which case they go from the gaseous state and they return back to the liquid state. That would be called condensation. These are opposite things. Evaporation is going from a liquid to a gas, condensation from a gas to a liquid. In order for something to evaporate, it must gain energy, and to condense, it must be losing energy. We're looking at, again, the bottom part of this graphic is more important, where it talks about if you go from a solid to a liquid, we call that melting. If you go from a liquid to a solid, that's freezing. It is at exactly the same temperature. It's a matter of, is the heat going into the system or coming out of the system? It's kind of like when you go through a door. The door doesn't change if you're going in or out. The freezing and melting temperature of water are both 0 degrees Celsius. Not slightly higher or slightly lower. They're the same temperature. Now, some other terms. A liquid going to a gas is condensing, but a gas going to a liquid would be, I said that backwards, excuse me. When a gas is going to a liquid, that's condensing. When a liquid is going to a gas, that's evaporation or boiling. The only difference is how rapidly those two processes occur. Boiling is a very rapid process. Evaporation is a very slow evolutionary process. Evaporation of water can happen at any temperature. Boiling will only happen at the boiling point. You could have ice outside on your sidewalk, and it might never get above freezing, but the sun can shine on that sidewalk, and the molecules on the surface will gain enough energy that they will turn from solid to a liquid and then even a gas and evaporate. And the temperature never went to the boiling point. So hopefully that makes sense, the difference between evaporation and boiling. And finally, if you go directly from a solid to a gas, you are undergoing, or the substance is undergoing, sublimation. If it goes from a gas to a solid, it's called deposition. This slide's calling it subliming both directions, but a better term, gas to solid, where it's never a liquid, is called deposition. Again, this is just a visual for you to think about. In a solid, the atoms are close together and basically not moving. In a liquid, the molecules are moving a little bit. They're still very closely packed together. And in a gas, the molecules are moving very rapidly, far apart, lots of space between them. Gases are compressible, and they must be contained, or they will escape from their container. Again, this is a little bit redundant, but solids hold their shape, have a fixed volume. Liquids take the shape of their container, and they have a fixed volume. Gases will take the shape of the container, and they will also take the volume of the container because they're free to move. So there's some solid ice there and are turning into liquid, and we know that would require heat, and a liquid turning into a gas, that would also require heat. When you take solid to a liquid that's melting, liquid to a gas, what's that called? Well, it could be boiling. What if it happens at a lower temperature? Evaporation. Good. This one sort of summarizes all of that stuff that we talked about. In the solid state, the part that we maybe didn't mention is the interactions between the particles are very strong. In other words, the atoms or molecules of the solid are strongly attracted to one another, which means they want to stay in the solid. In the liquid state, they're relatively strong. They want to stay there, but if you give enough heat, they're going to leave. And for a gas, there's basically no attraction between the individual molecules, so they are free to go whenever they have a chance. All right, so let's just define evaporation one more time for you. In order to evaporate, the molecules have to have enough energy to break those intermolecular forces. Those are the forces between the individual molecules. Once the heat is enough to rip them apart, then they will escape. The molecules of the surface break away, and they can become a gas if they have enough kinetic energy. Because energy had to go in to make this process occur, it is called an endothermic reaction, meaning energy goes in. In contrast, an exothermic reaction, heat would be released. Evaporation is a cooling process. See, if you are in the shower and you get out of the shower and you have water in your body, that water might evaporate off of your body. The water is changing from a liquid to a gas. That requires heat. Some of that heat comes from the room, but more of that heat comes from your own body. And if you lose heat, you say you feel cold. So there is no such thing as cold. There's either more heat or less heat, but process of evaporation is a cooling process. Sometimes they sell different pieces of cloth you can wet, you put on your head, and they help you feel cooler very quickly, right? Because again, as the water evaporates away, that's a cooling process. All right, so we watched those evaporate, and again, you did not have to hit the boiling point for evaporation to occur. It's just if some of these molecules leave, that's considered evaporation. Condensation is just the reverse. Everything I said just gets reversed. It's changing from a gaseous state to a liquid, and it's going to, if you were to cap this, it's going to try to achieve a balance or a dynamic equilibrium. And think about that as relative humidity. Some days it's like really humid, 85% humidity out, and that's as much water as can be held in the air in that dynamic equilibrium at that particular temperature. Other days it might be only 25% humidity in the air, and your skin might feel very dry at that under those conditions of dynamic equilibrium. So what is a closed system? A closed system is one where nothing comes in or out of what you're studying. So a closed system means matter can't come in or out of this flask. So I would have to put a rubber stopper or a cork on there for it to achieve dynamic equilibrium. So what the heck is this dynamic equilibrium all about? All right. Well, once this container is sealed, some of the molecules in the liquid state will go to the gas, some will go from the gas to the liquid, but after a period of time, it will achieve a steady state. There might be, let's say, 5 molecules of water in the air at all times. So there might be 10, but as soon as there's 10, 5 come out. So that's what the dynamic equilibrium means. The rate at which the molecules evaporate and condense are equal at dynamic equilibrium. It's sort of like you're running on a treadmill. As long as you're moving at the pace that the treadmill is moving, you're not really going anywhere. If you run too slow, you're going to get thrown off the treadmill. If you run too fast, you're going to bump into the treadmill, and you're not at a dynamic equilibrium. All right. I'm not going to ask you a bunch of questions about dynamic equilibrium, so I'll simply mention that dynamic equilibrium is when the rate that things are turning to a gas, vaporization, is the same as the rate of condensation. Molecules, remember, are in constant motion. They're dynamic. That means they're moving all the time. the total amount of liquid and vapor remains at a constant rate. That's why we use the term equilibrium. Vaporization, again, that's liquid turning to a gas, is required energy. It is taken or required to pull the molecules apart. If they're in the liquid state, they want to stay in the liquid state until you give them enough energy. That's the reason we sweat, to cool our bodies. That's one of the ways the Earth loses heat as well, is through the evaporative process of the oceans. Otherwise, it would just heat up and heat up and heat up, and that heat would be trapped here. Vaporization is then an endothermic process. It requires heat for it to occur. When I say endothermic, I'm saying that energy is going into the system. Okay? And even though energy is going in, a lot of students are like, but you said it's going to be feeling cooler. Well, you have to look at the system and the surroundings. The surroundings are putting energy in, and that's what's occurring there. All right, well, let's look at this one. This will summarize this for us pretty well and make sure we understand the terms. So we got solid, liquid, gas. If you go from a solid to a liquid, obviously that is melting. If you go from a liquid to a solid, we call that freezing. If you go from a liquid to a gas, we're going to call that vaporization. It could be evaporation or boiling. Vaporization covers both. And if you go from a gas to a liquid, that's condensation. If you make a direct flight from solid to gas, now there's not a lot of materials that can do that. Dry ice, carbon dioxide is one, iodine is another. Outside of that, I would be hard pressed to name a third substance that can undergo sublimation. If it goes directly from a gas to a solid, we call that deposition. That's how diamonds are actually made. For synthetic diamonds, they heat carbon up very, very hot till it turns to a gas, and then they let it coalesce and settle back down, and it makes diamonds. That's how you can make gem carbide saw blades that have diamonds on them. They're just as hard as naturally occurring diamonds, but they're not as pretty and not quite as valuable. So out of everything I said, make sure you know those terms and can apply them for this lesson. All right, we're going to deal with heating curves when we get to calorimetry, so I'm going to stop here for right now. Thanks for listening. Bye-bye.